那我们就开始吧。
OK，
Good morning, everyone. Good night, Professor Liu. Welcome to our analysis seminar. Today, Professor Shibo Liu, Xiamen University. We will talk as locking, linking, and indefinite Schrodinger equations. Professor Liu.
OK， it's my pleasure to have this opportunity to present this talk here. I am very grateful to Professor Zhou for his invitation and his arrangement. I am very happy to meet everyone here. Good morning, everyone. I will talk about local linking and some existence result for indefinite Schrodinger type equations. So this is the content of my talk. There are 5 sections. The second section is about semilinear Schrodinger equation, and the third and the fourth are about Schrodinger Poisson systems. Finally, in the last section, I will talk about quasilinear Schrodinger equations. In all these results, the Schrodinger operator is indefinite. Okay. So the first section is some basic idea about variational methods. So suppose omega is a bounded domain in Rn, and we consider this a Dirichlet problem. We define this functional f over the Sobolev space H01. Here, capital G is the primitive of the nonlinearity, the small g. Then, if U is a critical point of f, then by direct computation, for every testing function phi, we see that the derivative of f at U as a linear continuous functional over H01 acting on phi, that is this derivative, which is the difference of these two integrals. So we see that U is a weak solution or generalized solution of our boundary value problem. So if the nonlinearity G is smooth enough, then by elliptic regularity, we know that these weak solutions are in fact classical solutions. So the problem of solving this boundary value problem is equivalent to finding critical point of the functional f defined here. The branch of mathematics about the existence of critical point and the estimation of its numbers are called critical point theory. Critical point theory, in addition to the classical extreme value theory, which concerns about the minimizer and the maximizer of a given functional, there are 2 other important theory. The first is the Minimax Theory, which includes mountain path theorems, saddle point theorems, and all kinds of linking theorems. The other branch of critical point theory is the Morse theory. The basic concept of Morse theory are critical groups and Morse inequalities. Critical groups describe the local behavior of the functional near isolated critical point, while Morse inequality described local behavior and the global behavior of the functional. But we will not use Morse inequality in this talk. We will encounter critical group later. Okay. Now this is the basic idea of variational methods, and now we go to our object of study, the nonlinear Schrodinger equations. So this is time-dependent Schrodinger equations. An important class of solutions for this time-dependent equation is the so-called standing waves, which are solutions of this form. So it is easy to see that to find standing waves is equivalent to find solution U of this equation. This is an elliptic equation over the Euclidean space Rn. So this is an elliptic equation, sometimes called stationary Schrodinger equations. Okay, And similarly, in other similar problem, we will encounter these systems of equation, nonlinear equation, and also these equations of this form. Okay, so these two problems, the system 3 are called Schrodinger Poisson systems, while the equation 4 is called quasilinear Schrodinger equation, because this term here makes the equation quasilinear. In all these three problems, there is a capital V here, which is called a potential function. This potential, the relation between this potential V and the original potential U in the time-dependent problem are given by this equality. Okay, so we see that even if the capital U is positive, if we want to find standing waves which large omega, then our V will be negative somewhere, so that the Schrodinger operator might be indefinite. Okay, so the study of these three kind of problem in the last decades, most study concerns the case that V is positive. When V is positive, this quadratic form is positive definite. So if the nonlinearity G is superlinear near zero, then when capital B, the quadratic form is positive definite, the zero function will be a local minimizer of the corresponding variational function of capital Phi, so that we can apply the mountain path theorem to get a critical point of Phi, therefore solutions of our equations or systems. But as I said before, if omega is large, capital V might be negative somewhere, so this quadratic form might be indefinite. So mountain path theorem is no longer applicable. So we are interested in the case that capital B is indefinite. We'll focus on this situation. So for the simplest problem we are interested in, that is this semilinear Schrodinger equation, the equation 2. For this problem, this is the most simplest one. The most interesting situation is the case that V is periodic. In this case, the spectrum of the Schrodinger operator consists of some disjoint closed intervals. So if zero lies in the gap between two intervals, then the positive space and the negative space of this quadratic form are all infinite dimensional. Therefore, such problems are called strongly indefinite. So for this case, the most famous result is due to Klazowski and Shujie. They obtained a solution for the semilinear Schrodinger equation, that is the equation 2, assuming that the nonlinearity G is subcritical. Subcritical means that the last limit as t goes to infinity in this line is true. And also they assume that the nonlinearity G is superlinear at zero. This is their first assumption. The second assumption is the so-called Ambolosity-Lyapunov condition, which says that there is a mu greater than 2, so that for every non-zero t, this inequality holds. So this assumption G1 or Ambolosity-Lyapunov condition means that the nonlinearity satisfies this condition. As t goes to infinity, gt divided by t goes to positive infinity. Therefore, such nonlinearity are called superlinear. So this is a superlinear problem. So the condition G1 plays an important role in the study of a superlinear problem. But there are many superlinear functions not satisfying G1. For example, this function, this is superlinear, but it violates G1 because G1 implies that this equality is true when mu is greater than 2. Obviously, our GT here could not verify that, could not satisfy this condition. So this nonlinearity does not satisfy G1. However, G1 is very important because under the assumption G1, we can easily obtain the boundaries of Palace-Smell sequence of the functional. Without G1, we don't know whether the Palace-Smell sequence is bounded. So in the last decades, there are some mathematicians interested in studying superlinear problem without assuming G1. So this result is due to Yongqing Li and his collaborator. they study this case that V is periodic and positive. Therefore, they are studying the definite problem. Using Nihali manifold, they obtained a ground state solution, assuming G0, and instead of G1, they assume G2 here. G2 says that this function eta is strictly increasing, and also they assume this limit. This limit is slightly weaker than the superlinear assumption. That is small gt divided by t goes to positive infinity. So this is the positive case without assuming G1. But for the strongly indefinite case, that is G0 lies in the spectral gap of the Schrodinger operator. This was studied by Shujie and Vetch in 2009. They obtained a solution assuming the same condition as Li and his collaborator, except that they allow V to be sign changing. So the problem is strongly indefinite. So why they use Pankov manifold? Because they don't, and the Nihali manifold, because we don't know whether the Pallas-Smell sequence are bounded. So the standard variational method, the standard critical point theorem, such as Mountain Pass or linking theorem, could not apply. So this is why they use this Nihali or Pankov manifold method. But as I said, without G1, our functional cannot satisfy Pallas-Smell condition. But in addition to Pallas-Smell condition, or in addition to Pallas-Smell sequence, we can also work with salami sequence. So a main idea of my work is that although we don't know whether Pallas-Smell sequence are bounded, maybe we can obtain the boundedness of a salami sequence because the salami sequence are better than Pallas-Smell sequence. So replacing Pallas-Smell sequence by salami sequence appears in many work, many researches. But for indefinite problem, in particular, for strongly indefinite problem, it seems no such work. So in 2012, I obtained this result. Assuming V, the potential V is periodic, G lies in a spectral gap. Therefore, the problem is strongly indefinite. And also, we assume G0 and G2 prime. G2 prime, we compare G2 prime with their G2. We see that their G2 require this function to be strictly increasing, while my G2 prime only require this function to be no decreasing. So we obtain the same result. We have a ground state solution. So the proof of this theorem is not dependent on Nihali or Pankov manifold as the work of Li and Shujie and Vetch. No, we use standard variational method. We consider this functional. Then solutions of our problem are critical points of this functional. So we want to find the critical point of this functional. So let x plus and x minus be the positive and negative space of this quadratic form in the functional, and define the set n and the capital M here. N is a sphere on the positive space x plus, and M is a half ball where phi here is an element on x plus. Therefore, M is a half ball in the space spanned by x minus and phi. Okay. Then, because under the assumption capital G is non-negative, therefore it is clear that phi is no positive over x minus. Because this term, this integral is positive, which is the minus sign, it is negative. So this term on the negative space is no positive. So phi is no positive on x minus. So using this, we see that the increment of phi over n will be greater than the supplement of the boundary of capital M, provided rho is small enough and R is large enough. That is to say, the functional. It is easy to see that the functional satisfies the linking geometry. Usually with this linking geometry, we have a Pallas-Smell sequence. If you can prove that the Pallas-Smell sequence is bounded, then it will converge weakly to a critical point, which might be the solution you want. However, as we because we do not assume G1, the Pallas-Smell sequence might be unbounded. This is the difficulty. But there is a result by Gongbao Li and Shujie. They say that their result ensure that there is a salami sequence at the level C, where C is a positive number. A salami sequence UN is a sequence satisfying these two conditions. So because salami sequence is better than Pallas-Smell sequence, I can prove that this salami sequence is bounded, and its weak limit is the critical point we want. So this concludes the proof. Of course, I could not present the detail of the verification of the boundaries of UN here. If you are interested, you might consult my paper. And that is the idea. The idea of this work is that Pallas-Smell sequence might be unbounded, but salami sequence might be bounded. So this is my first result I want to share with you. So next I will go to the Schrodinger Poisson systems. So the system 6 here is the Schrodinger Poisson system. This is there is two unknown function u phi. But Benchy and his collaborator Fortunato, they proposed reduction method. So they defined this functional capital phi. Here, this term phi u is the solution of the second equation. Okay, in the system. Actually, phi u has this expression. Okay, so if u is a critical point of phi, then using u to solve the second equation, you obtain phi u, then the pair u phi u will be a solution of this system. Therefore, solving this system is equivalent to find the critical point of this functional phi. So this is the idea initiated by Benchy and Fortunato. If v is positive, then there are many results. It is I will not list the results here, but we are interested in the case that v is negative. Then this quadratic form might be indefinite. Okay, so other people study the case that this quadratic form is positive, but I will study the case that it is indefinite. So is this similar to the semilinear case I just showed you? No. Because there is a new feature arise in finding critical point of this function. What's the new feature here? Because there is a term here, this term. So without this term, if this quadratic form is indefinite, then the function might satisfy the linking geometry and we can apply the linking theorem. However, because this term is positive, so phi no longer no positive on the negative space. This is no longer true. This thing is no longer true. Without this, we could not verify this inequality. So the function of phi, in fact, does not satisfy the linking geometry. Linking geometry means that this inequality hold. Therefore, for this indefinite problem, we could not apply the linking theorem. So this is the new feature for this problem. So fortunately, there is a notion introduced by Jiaquan Li and Shujie Li in the 1980s, which is the so-called local linking, which the idea based on local linking might help us find the critical point of this phi. So let's have a look on what is local linking. Suppose X is a Banach space which can be decomposed as this sum, and phi is a functional. We said that phi has a local linking at 0 if there is some epsilon such that this inequality hold. This means that 0 is a local maximizer of the functional over the X minus space. And also we also have this. This means that 0 is a strictly local minimizer of the functional restricted to the X plus space. If these conditions are satisfied, we say that phi has a local linking at 0. Obviously, when phi has a local linking at 0, 0 is a subtle point of the functional, clearly a critical point. But we are interested in the no-zero critical point. Okay, so this is the concept local linking. Which local linking, we have this critical point theorem due to Shixia Luan and Anmin Mao. Their theorem says that if phi has a local linking and satisfies some salami type compactness condition, and phi map bounding set to bounding set, and for every finite dimensional subspace of the X plus space, phi is anti-cohesive along the anti-cohesive on the X minus and on the sum of X minus and Y. Okay, if these are satisfied, then phi has a non-zero critical point. We will use this theorem to solve our problem. Later we observe that local linking can be combined with Morse theory, which will simplify the many argument. So we will introduce some basic concept about Morse theory. Suppose phi is a continuously differentiable function and U is an isolated critical point. This set phi say is called a level set. Then this homology group, is the critical group of phi at the critical point U. So this is what critical group is. Here is the singular homology group of this topological pair. By the existence property of a singular homology, we know that the critical group at U describe the local behavior of the functional phi near the isolated critical point U. Okay. And how about the global property of the functional? The global property is described by the critical group at infinity. Now we assume that phi satisfies Pallas-Smell condition or salami condition, and alpha is a lower bound of the critical values of phi. Then this homologic group is the critical group of phi at infinity. Here, for different alpha, because if the alpha is a lower bound of critical value, when alpha changes, there is no critical value between. So all the different phi alpha are isomorphic. All the different alpha are homotopically equivalent. Therefore, by the homotopic invariance of homology, we know that the right-hand side does not depend on alpha. Therefore, this definition is well defined. Okay, so this is critical group at U describing local behavior of phi near U, and the critical group at infinity describe the global behavior of the functional. Okay, so using critical group, we can write the Morse inequality, but we will not need Morse inequality in this talk. But we need this critical point theorem due to Bach and Li. So if phi satisfies compactness and for some index L, the critical group, the L's critical group of phi at 0 and at infinity are not identical, then phi has a non-zero critical point. This is mentor in the rest of this talk. But to apply this result, we need to know something about the critical group, for example, at 0. So to get some information about the critical group at 0, we have this result due to Jiaquan Liu. So if phi has a local linking at 0, and the dimension of X minus is finite, say L, then the result is that the L's critical group of phi at 0 is non-trivial. So this result is very useful in the rest of this talk. Okay, this is the preliminary of the rest of this talk. Now we will start our investigation of Schrodinger Poisson systems. So this is the Schrodinger Poisson system we want to study. The first result is a joint work with my student published in 2015. So assume that this V is cohesive and that the nonlinearity G is subcritical. Subcritical means that this limit, when t goes to 0, when t goes to infinity, the limit is 0. Because here 6 is the critical exponent in dimension 3. And also we assume that G is superlinear at 0. And we also need this assumption G1, which is slightly, which is somewhat similar to the Ambolosity-Lobanovich condition, but weaker, okay? And also we assume that the nonlinearity is 4 superlinear. Then if 0 is not an eigenvalue of this Schrodinger operator, then our system has no trivial solutions. Why no trivial solution? Because it is easy to see that U equal to 0, phi equal to 0 is a trivial solution for this problem. Therefore, we are interested in no trivial solution. Well, this is a set of sufficient conditions to ensure the existence of no trivial solution. This should be the first result for the indefinite case, because we only assume that V is continuous and cohesive. The lower bound of V might be negative. V might be negative somewhere. Therefore, the Schrodinger operator might be indefinite. So this is the first result for indefinite case. Okay. So let's have a look on the proof, the basic idea. The first is to introduce a suitable working space. So we choose this subspace, linear subspace of the Sobolev space equipped with this norm. Here V tilde, because V is side changing, therefore we need to lift V tilde so that this is positive to make this norm. Then which this norm X is a Hilbert space which can be compactly embedded into the big space for P in this range. This is all standard result. Now we want to find a critical point for this functional. Okay. So firstly, for any epsilon positive, we have say epsilon. By our assumption on the nonlinearity small g, this is easy. So using this result, it is immediate that when u goes to 0, the integral of capital G is a higher order perturbation, which is back to the square of the norm of u. And also we know that this term, which is phi u here, is controlled by the fourth time power of the norm of u. Therefore, using this estimate, we see that our functional as u goes to 0, our functional is a quadratic form with higher order perturbation. That is phi u behave in this way. So it is clear that phi has a local linking at 0, because this higher order term you might ignore it because the main role was played by the first term. So the first term on the positive space it is positive, on the negative space is negative. So 0 at 0 is 0. Therefore, it has a local linking. Okay. So this is the proof of local linking. Now we can also prove that phi satisfies the compactness. I'm sorry that I have to omit this part here. And also we can prove that phi is anti-cohesive over the sum of any finite dimensional space of the positive space and the negative space. Okay. In fact, in our case, the negative space is finite dimensional. So this space here are all finite dimensional. So it is easy to prove its anti-cohesiveness. Okay. So the theorem implies the existence of no trivial solution, critical point of phi. Therefore, concluding the proof of this result. Okay. In this result, this compact embedding is important to ensure the ceramic condition here. Okay, but we can also study the case that the working space could not compactly embed into the big space. That is our result in 2017. Now we assume that V is bounded. Because V is bounded, the Schrodinger, the working space can only be H1 itself. We could not work on a suitable subspace to obtain the compact embedding. Okay, and we assume that this is S is no degenerate, and the negative space is finite dimensional. Okay, this is the assumption on V, and G for the nonlinearity, the assumption is similar to the previous theorem. But eventually we need the functional to satisfy compactness condition. But because the working space could not embed it into the big space compactly, we need some additional assumption on the nonlinearity. So the nonlinearity, we assume that it satisfies this condition G2. G2 is borrowed from the work of Bach and his collaborator. That is this paper in 2004. This is our assumption G2. Okay, this G2 means that G decay to 0 in some suitable manner. Okay, so under this assumption, our system, our Schrodinger Poisson system, also has a no-trivial solution. A typical example for a nonlinearity G satisfying our assumption is this function G. Here AX is a continuous positive function decaying to 0 at infinity, and P is greater than 4 and less than 6. Okay, so this is an example. So the proof of this theorem is somewhat similar to the previous theorem, but we need to deal with the compactness case condition because we do not have compact embedding anymore. And also, the proof is done by using critical group. We will not apply this theorem for the proof of our result because using critical group will be more convenient. So firstly, we prove the parallel Smell condition. So we choose parallel Smell sequence UN because our phi is indefinite. Is indefinite. We write UN as the sum of its projections on the negative space and the positive space of the quadratic form. Then, because the negative space is finite dimensional, this is important, and we can show that UN is bounded, and the proof is also omitted here. Therefore, up to a subsequence, it converge to weakly to some point U. Then, to obtain the strongly convergence, we define this functional capital N. So we know that by the result of Zhao and Zhao, we know that N is weakly lower semi-continuous, and the derivative of N is weakly sequentially continuous. So this lower limit precisely is this. So it is no negative. Also, using the condition G2 by the argument of Bach, we know that this upper limit is no positive. Combine this fact, UN is parallel Smell sequence, and this is no negative, and this is no positive. We can obtain that the norm of UN goes to the norm of U. But UN converts to U weakly. Therefore, actually, UN converts to U strongly. So this verifies the parallel Smell condition. Okay, this is the first step. Then as before, we can prove that phi has a local linking at 0. Phi has a local linking at 0. So by the result of Jiaquan Liu I just mentioned, if the dimension of the negative space of the quadratic form x minus is L, then we know that the L's critical group of phi at 0 is no trivial. We can also prove that the critical group of phi at infinity are trivial for every L. Okay. For the next result, I will demonstrate how to obtain the result in this of this type. Therefore, the result of Bach and Li provide us a no-zero critical point. So this no-zero critical point gives rise to no-trivial solutions for our system. So this concludes the proof. So in these two theorems, the nonlinearity G are all 4 superlinear. Gt divided by T to the cube goes to positive infinity. We also have a result that G is not 4 superlinear. This is a joint work with Mosconi. So V is superlinear as before, and 0 is not an eigenvalue. This is a non-degenerate assumption. For the nonlinearity, we assume that it is subcritical superlinear at 0 as before, but we assume that G is controlled by this power function. Here, P is greater than 2 but less than 3. So because P is less than 3, our G could not be superlinear, could not be 4 superlinear. Okay. Under this assumption, this system has 2 no-zero solutions. Here is an example. The power function which put P in this range. Okay. So this is our result for the case G is not 4 superlinear. We can also study the case that P is greater than 3 but not greater than 4. In this case, we can, which additional assumption, Pós-graduação type assumption under the potential V, we can have a no-zero solution. Okay, but I will omit that part. Okay, I will not prove this theorem here, but motivated by this theorem, we study the Schrodinger-Kirchhoff problem. That is this problem. This problem is also variational. The solution can be found as critical point of this functional. Okay, so this is our recent result. Suppose 0. We know that under our assumption, the Schrodinger operator has a complete sequence of eigenvalue. So suppose 0 lies between 2 eigenvalue, and V is continuous as before, and outside a big ball, V behave in this way. So here gamma is greater than 1. So V not only is cohesive, This assumption is stronger than the cohesiveness of V. Unlike the previous result, we need this result. I will explain why we need this result in the next page. So this is the assumption on V. And for the nonlinearity G, G is superlinear at 0 and sub-quadratic at infinity. Then this problem has two non-zero solutions. Our problem has two non-zero solutions. If G is odd, then we have k pairs of non-zero solution, where the k is the index of this eigenvalue. Okay. So in this theorem, under the assumption of this theorem, we will prove that phi is cohesive as the proof of this theorem, which is Mosconi. Our functional is cohesive. The cohesiveness of this functional phi since nature, because this term is of power order 2, and this is fourth order, and because G is sub-quadratic at infinity, capital G will be sub-cubic at infinity. Therefore, this is the higher order term. It is positive. So it seems that the cohesiveness of phi is nature, but actually this is not obvious, because even if the V is positive and capital G grows in this way, where P is not greater than 4, then in this assumption, this is still the highest order term, but the function is unbounded below. The increment is negative infinity. So the cohesiveness of this functional is not obvious. So to prove this cohesiveness of this functional, we compare. This work is motivated by this work. In this work, we are studying this functional. For this functional, this inequality of Lewis is very important. So we need to find a similar inequality for our functional corresponding to this Schrodinger Poisson system. Okay. But for Schrodinger Poisson system, we do not have this term. So we need to solve this problem. The first step is choose the working space as before. Lifting V, make it positive so that we can define the norm. Then this space, by our assumption of V and using Horde inequality, we have this. Now, because our gamma is greater than 1, and we are working in 3-dimensional space, so this integral converge. Therefore, we obtain this inequality. This inequality will provide us a continuous embedding. Will provide us a continuous embedding from our working space X into Lebesgue space L3/2. Okay. Using this continuous embedding, applying the Gaglioli-Nylenburg inequality, we have this inequality. And then using the Young inequality, and now using the continuous embedding we just established, we eventually obtain this inequality. So this final inequality will play the same role as the Lewis inequality for the study of Schrodinger Poisson systems. Okay. So this is our result on Schrodinger-Kirchhoff problem. And finally, I will talk about our result on quasilinear Schrodinger equation. That is this problem. This equation is the Euler-Lagrange equation for this functional. However, this functional could not be defined on the whole space H1, because for some u in H1, the integral of this term might be infinite. So for such u, J is not defined there. So J can define on a proper subset of this space. There is no critical point theorem to deal with such functional, not defined on the whole space, but defined on a proper subset of the space. So this is the main difficulty for the study of this quasilinear problem. But in 2003, Jiaquan Liu, Ziqiang Wang, and their student introduced a nonlinear transformation. Their nonlinear transformation later was improved by these two French mathematicians in 2004. So using this nonlinear transformation, we can consider this quadilinear problem is converted to a semilinear problem, whose solutions are critical point of this functional capital phi. So if V is a critical point of phi, then applying the nonlinear transformation f to V, we obtain a function u. This u will be solutions of our quadilinear problem. Okay. So since since they introduced this nonlinear transformation, this method has been applied numerous of times by many mathematicians, and many interesting results on this quadilinear Schrodinger equation appears in the literature. But all the results require that the zero function to be a local minimizer of this functional capital Phi. Every paper requires V to be local minimizer. For example, if capital V is positive, if the potential V is positive, then the zero function will be a local minimizer of this functional. So as before, we are interested in the case that if V is side changing, so that zero function is not local minimizer anymore. The reason for studying this problem is the same as our previous result on Schrodinger Poisson system. Of course, also including the semilinear Schrodinger equation. Okay, and our Schrodinger-Kirchhoff problem we just talk about. So how to deal with this case? We may think we might try to apply the local linking as our study of Schrodinger Poisson system and the Schrodinger-Kirchhoff problem, but we notice that the principal part of this functional is not a quadratic form, because f is nonlinear here. So this is not a quadratic form of V. So without this quadratic form, we don't know how to decompose the space. No matter you want to apply the linking theorem or local linking, you need to decompose the space into the direct sum of two subspace. But if you do not have a quadratic form, how to decompose the space is not clear. So this is the main difficulty of this problem. Okay. Of course, we can decompose the space using this quadratic form, but this quadratic form does not appear in our functional capital Phi. So we don't know such decomposition. We don't know the relation of such a decomposition which the investigation of our Phi. Okay, so this is the difficulty. Also, to study the boundaries of asymptotically critical sequence, Pallas-Smell sequence, salami sequence, we need to decompose the space, projecting the decompose the sequence as the sum of their projection on negative space and positive space, just like the proof of our result about Schrodinger Poisson system. Okay, we have this decomposition. We just mentioned this. Okay, so for our quadilinear problem, this decomposition seems useless because the nonlinear transformation here will destroy this decomposition. Okay, we don't know we don't know what is the result to apply the f to this sum. Okay, so this is also difficult. Fortunately, which is slightly stronger condition, we can obtain some existent result. This is our result in 2018. As before, V is cohesive, and for the nonlinearity G, which we assume that it is superlinear at zero and subcritical. This is subcritical. But for this problem, subcritical means that P is less than twice of the usual critical exponent. Okay, this is due to the nonlinear transformation, due to the behavior of the nonlinear transformation f at infinity. And also we assume this G1 condition, which is essentially unvelocity novelty type condition. Then if 0 is not an eigenvalue, we will have a no-trivial solution for this quadilinear problem. Okay, so this is the first result for indefinite quadilinear Schrodinger equation in the literature. So to prove this result, firstly we set up the functional framework, define this working space as before, and as before it can be compactly embedded into Lebesgue space for Q in this range. So we want to find the critical point for this functional. Okay. Firstly, we can ensure that this function satisfies the salami compactness condition using our condition G1. G1 is the unvelocity Lyapunov type assumption. So using G1, we can prove that the salami sequence are bounded. Okay, salami sequence are bounded, and then using the compact embedding, and also using some argument from the work of Wu Xian, Wu Xian 教授, Professor Wu Xian. The work of Wu studied the definite case. In the work of Wu, the potential V is positive. But now we study the sign changing case. Okay, so this is different with the work of Professor Wu. This is the first step. Our phi satisfies compactness condition. Then we investigate the behavior of phi at infinity. So using the property of the nonlinear transformation and using our assumption, we can prove that if A is large enough, then when we in this when we is chosen from this level set, that is phi not greater than negative A, then this derivative is negative, strictly negative. And also for every W on the unit sphere that is along any direction W, phi is unbounded below as S goes to positive infinity. Therefore, there is a unique SW such that this equal exactly negative A. The arriving time start from the unit sphere, you go along the line, you will decay to negative infinity. Therefore, you will touch minus A. But the arriving time is unique, denoted by SW. Okay, and using this negativeness of the derivative at the arriving time is also negative. Therefore, we can apply the implicit function theorem to the equation phi SW equal negative A. We see that at the arriving time SW depend continuously on W. So this function is continuous. So having this continuous function by standard argument, initially due to Jiaquan Wang, in his famous work in 1991, we can construct a deformation from the complement of the unit spore to the level set. Therefore, by the definition of critical globe at infinity, this homology, because this is the strong deformation from this to this, means that these two sets are homotopically equivalent. Therefore, by the homotopically invariance of homology, we know that these two homology globe are isomorphic. But X is infinite dimensional. Therefore, we know that for all index I, this homology is trivial. So we have complete our investigation of the critical globe at infinity, or the global behavior of phi is trivial. Okay. The last step for our proof is to study the behavior of phi near zero. We hope to have a local linking, but our function is of this form. Of this form, there is no quadratic form to work with. How to decompose the space and verify the local linking? This is the most important element of this study. So, fortunately, although our functional is only say one, because small g is only continuous, so this function is only say one. The principal part that is this part is say two. This part we denote by capital Q. Capital Q is say two, and using the property of the nonlinear transformation, we can compute the derivative of Q at a zero function. The first order derivative, the second order derivative is given by this bilinear form. Okay, so having computing the derivatives, we can apply the Taylor expansion. As v goes to zero, our QV will be the zero order term plus the first order term and the second order term and the higher order perturbation. So this is precisely the quadratic form, which is higher order perturbation. Now our function of capital phi is QV subtract by this integral of capital G. Then the integral of capital G is also higher order perturbation. In conclusion, as V goes to 0, our functional capital V behave like this no-degenerate quadratic form, adding this higher order perturbation. So it is now clear that phi has a local linking, which leads back to the decomposition. Here, x negative and x plus are the negative and the positive space of this quadratic form. So as before, we know that the L's critical group of phi at 0 is not trivial, where L is the dimension of the negative space. Therefore, the critical group of phi at 0 and infinity are not identical. So since the functional satisfies the salami condition, we can obtain a non-zero critical point, which will give us a non-zero solution for our quasilinear, for our indefinite quasilinear Schrodinger equation. Okay, so this concludes the proof. The final remark: in 2019, we study a related problem. This is a first order problem. So this problem, since this equation seems much more complicated than the quadilinear Schrodinger equation we just discussed, because in addition to every term, there is a biharmonic term here. Okay, so this equation seems more complicated. But actually, the study of this first order equation is easier than the previous second order quadilinear Schrodinger equation, because solution of this equation are critical point of this functional phi, defining H2. But unlike the case of quadilinear equation, for quadilinear equation, the natural functional could not define on the whole space. It is only defined on a proper subset of the space. Well, for our first order equation, since we are working on H2, and the H2 is more regular than H1, so we don't need to make a nonlinear transformation. This function, capital phi, is well defined on the whole space H2. Of course, this is true only for dimension not greater than 6. Okay, so since we don't need to make a nonlinear transformation, we can get better results. Okay, so for example, we can deal with the case that the potential is bounded, so that the working space is precisely H2, so we do not have a compact embedding. So why we can get a better result? Because without involving the nonlinear transformation, the principal part of the functional is a quadratic form. So it is obvious how to decompose the space to verify the linking or local linking we need for treating indefinite problem. Okay, so this is the advantage to have this higher order term. Okay, okay, this I will omit. So this is what I want to report about our result in this direction. So my concluding remark is that in all this result, except the result about the semilinear problem, except the result for semilinear problem I talked about at the very beginning. In other result, all our results require the functional to satisfy Pallas-Smell condition or salami condition. So why we need so strong insurance for the study of the functional? Because currently, for if the functional only has local linking, all critical point theory and the theory require the functional to satisfy the global compactness. Unlike the as I said before, for the critical point theory, we have a minimax and a Morse theory. So minimax in multipath or linking, if you do not have a global compactness, you still has a Pallas-Smell sequence. You might investigate its boundedness and the convergence, whether it is convergence. Okay, so even if you do not have global compactness, you have a asymptotically critical sequence, such as Pallas-Smell sequence or salami sequence. But for result involving local linking, if you have global compactness as our result, you will have a critical point. But if you do not have a global compactness, of course you do not have critical point, and you also could not have a asymptotically critical sequence. So this is very different from the result using minimax argument such as mountain pass and linking. So this is the reason why we need our functional to satisfy global compactness. Okay, so this is what I want to talk. Thank you very much. Thank you for your attention.
Thank you, Professor Liu.
Thank you.
Any questions?
I would like to ask a question.
Yeah.
Thanks, Professor Liu, for this very nice talk, an overview of all of the method and applied to many different problems. Thank you. It was very interesting. My question is, in the very, like the frame 23rd, you define a quadratic operator in this type of Collin-Jean problems with the
23rd. Yeah.
In the very end.
Very end, yes.
Yeah, here.
Yeah.
Why in this quadratic form you don't have the term with f of v? Because before.
Let me show you.
If you go
so
here,
this is
here,
yes, this is the capital Q. You said why we do not have f here. Yeah, yes.
Yes, why you do not have f?
This is you see the nonlinear transformation f has this property. F0 is 0, and the derivative of f at 0 is 1. So this is the nice property of f. Therefore, when we take the derivative and evaluate at 0, f disappear. So
okay.
So, yeah.
Nice.
Yeah, this is
so you go back to the norm and then you can work with the norm.
Yeah. So this is the
because you are
lucky fact
around
fact
around 0.
Yes. Very lucky.
Nice. And my other question is, you, at least in most of your problems, you have v of x going to plus infinity. So it's like a coercive potential.
Yeah, coercive.
And this gives you a finite negative spectrum, right?
Yeah, yes. Sorry, can I change a slide so that I don't need to step by step? I can display the whole page immediately. I will change my slide. Okay, I will stop the sharing this. Sorry.
So in your problems, you always have a finite dimensional negative spectrum.
Yes.
Right.
Why we need? Can you see the slide? Yeah.
Yes.
Yes. So to save time, I will not change. So because why we need why we can only deal with finite dimensional, because for example, if we use the critical group, you know the homology. The tool is here is the singular homology. Singular homology could not detect infinite dimensional sphere. Okay, the finite dimensional sphere is homologically non-trivial, but the infinite dimensional sphere, from the homological point of view, is trivial, topologically trivial. So this, so using this type of critical group, we can only deal with finite dimensional. We can only detect finite dimensional. Yeah, this is the key, the essential reason why we can only deal with finite dimensional negative space.
Okay. Thank you very much. Very nice.
Thank you.
Results.
Very good. Any more questions? No questions? 那我们以后再讨论。 Thank you very
thank-
much.
Thank you everyone for your attention. Thank you. So I will stop. I will stop sharing the screen. Stop. How to stop?